which is horrible if you were not. You need this handout on writing PSIs. We talked about this in detail in discussion class this week. And in order to make all this stuff organized, concise, and I hope clear, we provided this handout sheet. Come get it if you didn't get it. Over here. And also today, to supplement Chem Notes 2, and to make you aware that this handout sheet will be given to you for every quiz and exam. A handout sheet you are to have with you at all times, so that as necessary, we'll have this information immediately available. Your job with respect to the information on this sheet is not to memorize it, but to know how to use it. The first aspect of which will be to write equations for Bronsted-Lowry acid-base reactions. So take a look at this handout sheet. There's a similar Bronsted-Lowry acid-base table in the notes, but the handout contains, the information sheet contains, a Bronsted-Lowry acid-base table that's far more comprehensive. The acids listed in the acid column are listed in order of descending strength. Actually, ascending strength. Simpler said, as the acids go from top to bottom, they get weaker. Bottom to top, they get stronger. In this table, you see the formulas for 5 strong acids. Because we've defined strong acids as hydronium ion or any acid stronger than hydronium ion. So the 5 strong acids in this table: hydronium ion, nitric acid, hydrochloric acid, sulfuric acid, and perchloric acid. Now, underneath hydronium ion, down to water, including water, are the acids which can be treated as weak acids in water solution and which show observable, measurable strength as acids in water solution. There's a couple of formulas listed underneath water in this table, in the acid column. Hydrogen sulfide ion, hydroxide ion. Anything which has hydrogen in its composition can theoretically be expected to behave as a Bronsted acid. Because of the hydrogen in its composition, you can imagine it being in a chemical environment in which it will react to give away H+. But as species themselves, hydrogen sulfide in water solution, hydroxide in water solution, do not to a measurable extent have the capacity to give away H+. Why not? They're weaker than water and they're grossly outnumbered by water. So they can't possibly get into the H+ giving game. Now look at the base column. Given that the acids are listed in order of strength from top to bottom, the bases must be listed in order of strength from... Wait, let me say this right. The acids are listed in order of strength from bottom to top. There, I got this untangled, now I can say it right. Consequently, the bases must be listed in order of strength from top to bottom. Notice the acid, pardon me, remember our strong acids in the acid column? Notice the conjugate bases of these acids, whose formulas appear immediately horizontal, position-wise, in the base column. Water for hydronium ion. Nitrate ion for nitric acid. Chloride ion for hydrochloric acid, etc. Those bases, which are conjugate bases of acids stronger than hydronium ion, cannot show measurable ability as Bronsted bases in water solution to capture H+. Interesting, isn't it? They have negative charges. Water is a neutral species. So we're finding out that water, a neutral species, has a greater, stronger capacity to grab H+ than these 4 negative ions listed above water in the base column. How about that? So you have to recognize right off the bat that the strength of a base does not necessarily depend upon its being an anion. Although from a natural Coulombic standpoint, any anion has a natural affinity for H+, because H+ is plus. But in water solution, these 4 bases, the bases of the conjugate bases of the acid stronger than hydronium ion, these 4 bases are not only weaker than water, they're grossly outnumbered by water, so they cannot, from a measurable extent standpoint, get into the H+ grabbing game in water solution. Now as we go down the base column, water, and on down to phosphate ion. That's the base position immediately above hydroxide ion. Those are the weak bases in water solution whose strengths can be observed. And they are, of course, the conjugate bases of the corresponding weak acids in the acid column. Then we get the hydroxide ion, and the only 2 bases which we have listed in this table that are stronger bases than hydroxide ion. There's no need for the table to be containing more information than that. Specifically sulfide ion and oxide ion. To what extent? In sodium sulfide solution, 1 molar. Write that on the board. You did this in discussions class, but it's important. Sodium sulfide is an ionic compound. So when you make this solution, at the minimum, sodium sulfide, the ionic compound, dissociates. Into what does it dissociate? Its component ions, Na plus and S double minus, the sulfide ion. Now comes the $64 question. What is the PSI for sodium sulfide solution? Tell me the PSI.
SH.
Tell me the formula and the charge. It's on this table. Nope. HS minus. So the PSI for sodium sulfide solution is Na plus, or if you wish, Na plus AQ, HS minus AQ. Water, of course, that's the solvent. And from an acid-base standpoint, what is the species we are principally concerned with in sodium sulfide solution? What is it? I'm listening. Hydroxide ion. Because when you put the sulfide ion in solution, the sulfide ion reacted with water, didn't it? And what did it do to water? Water, the weak acid. Sulfide ion reached over to water, the weak acid, and said, I'll have one of your H pluses, please. So as to convert sulfide ion to hydrogen sulfide ion and water to hydroxide ion. What's the extent of this reaction? Practically speaking, 100%. So independent of the fact that this is the label on the bottle, if you write a PSI for this solution, and you write this, which is what the textbooks write, you flunk. Because you just wrote the formula for something which ain't there. How can you stipulate that this is a component of the system when it ain't there? It all reacted. It all converted to HS minus and hydroxide ion. Same for oxide ion.
Why doesn't it continue to H2S?
Pardon?
Why does it continue to form H2S?
Why does it or does not?
Why doesn't it?
Doesn't it not? We'll talk about that in a few moments. You got to let us get a little bit further before we answer that question. Now then, this of course is part and parcel of the rules of the road for writing inventories correctly, PSIs correctly, for water solutions of Brownstein-Lowry acids and bases, both weak and strong. Now then, there's one other special acid, or type of acid, which we talked about in brief last gathering. But from the reaction I got from the class, I got the impression you didn't talk about this in sufficient detail on Tuesday to know what we were getting at with respect to this particular special type of acid. So there's another label. To prepare this solution, per liter volume of solution, I dissolve 1 mole of aluminum nitrate. What kind of compound is aluminum nitrate? Ionic, molecular? Ionic. That means aluminum nitrate on dissolving in solution at the minimum did what? Dissociated. Now then, with that information at hand, write the PSI for this solution. And to assist you in writing this PSI, I will ask that you take a look at the acid column in the acid-base table on the info sheet you just picked up. What is the formula for the aluminum-containing component of this system? You got it. Aluminum ion. A positive ion with a substantial positive charge density. What's the consequence of dissolving an ion of substantial positive charge density in water solvent? This ion, because of its substantial positive charge density, exerts a strong coulombic attraction on the negative charge density of surrounding water molecules. The negative charge density of water molecules rests on the oxygen atom component of the water molecule. Upshot, the negative end of the water dipole, the oxygen atom end, and the ion, the positive ion with the substantial positive charge density, come together. And in so doing form a coordinate covalent bond. And in the case of aluminum ion, form this well-defined hydrate. Now at this stage of the game you might ask, why is it a 6 hydrate instead of a 5 or a 4 or an 8? We'll talk about that later, not now. For now, I ask simply that you take a look again at the acid-base table. Recognize the presence of a number of well-defined hydrated metal ions, each of which have measurable Bronsted acidities in water solution. In this table, beside hydrated aluminum ion, we've got hydrated iron plus 3, hydrated zinc plus 2, and hydrated magnesium plus 2. In addition to these hydrated metal ions, you'll study other hydrated metal ions and their chemistry with the work you do in 46 laboratories. But for our purposes in lecture, this small collection of hydrated metal ions, which behave as Bronsted acids, is adequate. Now, back to what we didn't finish yesterday. Wednesday, but started. Two molecules, methanol and methyl hydroxylamine, each of which as pure liquids have been used as solvents for Bronsted-Lowry acid-base studies. Now, the vast majority of Bronsted-Lowry acid-base chemistry is investigated in water solvent. But chemists, in order to learn more, have conducted Bronsted-Lowry acid-base investigations in solvents other than water, like liquid ammonia. And the leveling effect tells us that in a particular solvent, from a Bronsted-Lowry acid-base standpoint, the strongest acid which can be found in a solvent, the strongest Bronsted acid which can be found in a solvent at high concentration, is always the conjugate acid of the solvent. And the strongest base which can ever be found at high concentration in the solvent is always the conjugate base of the solvent. Upshot, hydronium ion, hydroxide ion are those species for water solution systems. For ammonia, ammonium ion and the amide ion, H2N-, formula we had on the board last time. For methanol, conjugate acid is formed by H+ attaching to one of these non-bonding pairs on the oxygen atom in the methanol molecule to make a coordinate covalent bond. You see any similarity to that chemistry to what we talked about over here when aluminum ion interacts with water molecules to make hydrated aluminum ions? Well, here H+ interacts with a non-bonding pair to make a coordinate covalent bond. Just like H+ in water solution interacts with the water molecule to make hydronium ion. Same idea. So we recognized